All right, let's take a look at our next section, 2.4, which involves symmetry. All right, there's three things we'll look for when we're looking at the symmetry of a graph. And that's is to have symmetry with respect to the x-axis, the y-axis, or the origin. So those are our three tests for symmetry. So let's talk about what it means to be symmetric to the axes of the origin. Starting with the x-axis, a graph is said to be symmetric with respect to the x-axis if for any point, any ordered pair, say x and y, so we've got a point xy on the graph, then the point x negative y is also on that graph. So xy gives us x negative y. All right, these are what we call our reflection points with respect to the x-axis. So we have these ordered pairs that reflect across the x-axis. So go down here to our three graphs below, and you see an example of each type of symmetry with these tests. And you can see what I'm talking about with this graph. So for example, here's an ordered pair on the graph here, say x and y. Well, if you look directly across the x-axis, right, here's the x-axis, we see that reflection point. Here's that ordered pair x negative y. Right, any ordered pair xy, we find the ordered pair x negative y. Right, for example, if that was negative 3, 5, this would be negative 3, negative 5. So those are what we call reflection points. So we're seeing these reflection points with respect to the x-axis. So that must hold true for all ordered pairs. So we can use our points to prove our symmetry. All right, as we go to y-axis, now graphically, again, a graph symmetric to the y-axis says for any point xy on the graph, then the ordered pair negative xy will be on there. So we've got xy, we get negative xy. These are our reflection points with respect to the y-axis. Now again, visually, we can easily see the symmetry. Right, and again, going back to the x-axis, right, the x-axis splits that graph right down the middle, cuts it in half to equal parts. Well, just like the second graph, right, we've got a graph in which the y-axis splits this graph right down the middle and cuts it in half in two equal parts. We have symmetry. But for example, if you look at any ordered pair on the graph that's symmetric with respect to the y-axis, if you reflect about the y-axis, you're going to find the ordered pair negative xy on there. Every ordered pair xy, right, we have the point negative xy. So you can see that here with these ordered pairs, showing that reflection property. So definitely symmetric to the y-axis. So every point xy, negative xy is on there. Now as we go to our origin, which is the point 0, 0, there's the origin, right? Any graph symmetric with respect to the origin, you pick any point xy on the graph, then you're going to find the ordered pair negative x negative y also on that graph. So now you're looking at the opposite of both coordinates. So for example, if you go to this ordered pair, let's take this point here, say xy. Well, if you look diagonally across the origin, you're going to be right back on your graph at the point negative x negative y. That's true for any ordered pair with respect to this graph xy. You can see that symmetry, right, with respect. So you see those ordered pairs, right, as we reflect across that graph. So again, if this was the point, let's just take, for example, maybe this is the ordered pair negative 1, 6. Well, over here would be positive 1, negative 6, right? We take the opposite of both coordinates. So those are reflection properties. And that leads us to our algebraic test for symmetry. So if we're going to test algebraically if a graph is symmetric to the x-axis, then we can go to our equation of that graph and replace y, right, an equation with x and y that produces these ordered pairs xy. We can replace y in that equation with negative y, and we should be able to simplify right back to our original equation. So our test variable is negative y with the x-axis, right? And that's a reflection property. So again, it comes back through the reflection points. If xy is on the graph, then x negative y is on there. So again, using reflection properties, so reflection points. And the same goes for the y-axis, right? If we're going to test for symmetry, we can go to our equation. We can find x, wherever we see an x term in our equation, replace it with negative x, and try to simplify back to the original equation, right? We can produce that reflection point, right? For every point xy, negative xy should be on there. We can show that from the equation, right? If we can get back to that original equation after plugging in that test variable of negative x. And at the origin, you do what? Both, negative x and negative y. So every ordered pair xy, right, produces the ordered pair negative x, negative y. So those are reflection points. So we're going to take that and go to some examples and look at proven symmetry. So let's test algebraically. And if you want, we can look at it graphically. If you would like, we can graph it and show it too. But let's take an example here, A. Now here's an equation that reads 5x squared plus y equals 3x fourth power. Now you might already know what its graph looks like. Maybe you graph it in your calculator and you already see what it has symmetry with respect to. But there's 3 tests. So let's start with the x-axis, for example. Is this graph symmetric to the x-axis? So remember our test. Every ordered pair, right, xy, we need to find the ordered pair x, negative y on there. Alright, so we're going to replace y with negative y. That's our work. Replace y with negative y. And then simplify. That's the work algebraically. So as we go to our equation, right, that implies we have 5x squared plus y, well, out goes y, in comes negative y. So you can see again that test variable. So plugging in negative y, right, into our equation. Now as we simplify, right, let's go ahead and simplify. As we simplify, we get what? 5x squared minus y equal to 3x to the fourth power. Now, any way to simplify back to the original equation, this is not the original, right? We have a different equation than we started with after we plugged in this test variable. Well, we could, if we want, just to show some algebraic properties. The only thing that's different is negative y. So we could multiply that by negative 1, but we'd have to multiply all 3 terms, both sides, by negative 1, use the multiplication property of equality. And that would give us what? Negative 5x squared plus y. Now, yeah, y looks good, but the x terms are off. So again, this is not the original equation. Can't produce it. So this implies it's not symmetric. It's not symmetric with respect to x-axis. So the x-axis isn't going to split this graph down the middle. Now let's go to the y-axis test. So with our y-axis, let's write down this test here. We'll do it in blue. For a graph to be symmetric with respect to the y-axis, every ordered pair xy should produce the ordered pair negative xy, right? Replace x with negative x and simplify. All right, see if you can get back to your original equation. That's our goal. So as we do that, well, what happens in this equation? 5x squared becomes 5 times negative x squared plus y equal to 3 times negative x to the fourth power. Well, as we simplify, and here's the key, we got this even power right here of 2 on negative x. So as we simplify that, what is negative x times negative x? It's positive x squared. Plus y. What's negative x to the fourth power? Negative x times negative x times negative x times negative x is positive x to the fourth power. Any even power on a negative base makes it positive. Right? If it's odd, it'd be negative. So based off those 2 x terms, which is where our test variable was, being even powers, it gets us right back to the original equation when we simplify. So now that we've simplified, we have our original equation in front of us. So with our original equation, right, we have symmetry. So I know, without even graphing it, and we can graph it here in a little bit, look at it. We have symmetry with y-axis. It's symmetric with respect to the y-axis. Every ordered pair xy produces negative xy. We've seen that with our test. And then we can go to the origin, right? We look at our origin test. All right, now the origin test says what? Every ordered pair xy should produce the ordered pair negative x, negative y. So you replace x and y with negative x and negative y and simplify. So we can get back to the original, like our last example with the y-axis. We have symmetry. Now as we do that test, we have 5 times negative x squared plus y. So wherever we see our variable, we're going to put in the opposite. So plus negative y equal 3 times negative x, 4th power. As I simplify, of course, negative x squared becomes x squared, plus negative y is a minus y. 3 times negative x to the 4th power, 3 times x to the 4th. Well, here's our term. That's all. It's not the original. Right? And we could multiply everything by negative, but it's going to mess up the x terms. So again, we can't get the original equation. It's not symmetric with respect to the origin. All right? So with that, we have one test for symmetry held true, and that was the y-axis only. So with example A, this is y-axis only for symmetry. All right, so let's go ahead and look at that graphically. So let's check graphically. Now, if you want to check it graphically, right, all we have to do is go to our calculator. Let's put it in graphing mode. So let's take this equation. So we have 5x squared plus y equal to 3x to the 4th power. So I would solve for y, right? We needed y equal form. So we would subtract the 5x squared over. So y would equal negative 5x squared plus 3x to the 4. So we could graph it now. So let's go put that in our TI. So get your TI calculator out. Right? Let's go take a look at the graph here, and let's show the symmetry that we just found. So on our TIs, we go to the y equal button. I'm going to store in negative 5x squared plus 3x to the 4th power. And I'm going to graph it. We can go zoom 6 on standard window. And what do you see with this graph? You see symmetry with the y-axis. Right down the middle, y-axis splits it into equal parts. And take it a little bit further, go to your table. If you go to your table, right, notice every ordered pair xy. So for example, take the point 3, 198. Here's an ordered pair on the graph of this function we've graphed. Well, look at its other ordered pair's reflection. Now we got the ordered pair negative 3, 198. So there's xy, here's negative xy. Right, 1, negative 2, we got negative 1, negative 2. Every point you see that holding true with this graph. Definitely symmetric with respect to the y-axis. All right, let's take example B here. Let's move to our next problem. Now, example B, as we look for symmetry. All right, in this one we've got an equation. It reads y equal to negative 4 over x. Let's see about our symmetry with it. So I'm going to start with the x-axis. So again, plug in our point. All right, every ordered pair, x, y, we should see the point x, negative y on there. So that implies y, well, that'll be negative y equals negative 4 over x. So right now my equation reads negative y equal negative 4 over x. And if I were to simplify, even if I wanted to multiply both sides by negative, it's still not my original equation. Right, I've got y equal to positive 4 over x. So again, not the original. So not the original equation means we don't have symmetry. So if you were to graph this function here as a rational function, it's not symmetric with respect to the x-axis. So it fails the x-axis symmetry. So it doesn't hold true with that one. Now as I move to the y-axis, let's see about y-axis symmetry. Well, y-axis, our reflection point is every ordered pair xy. We produce negative xy. So let's plug in negative x where we see the x terms. So y is equal to -4 divided by negative x. And as we simplify, so again, make sure we do our simplifying step. And as we do that, we get what? Y equal to -4 over negative x. Two negatives make a positive. So that simplifies to y equal 4 over x. Again, not our original equation. Right? It fails the y-axis symmetry test. So right now we have no symmetry, which is possible. Maybe there's no symmetry with this graph. So again, not symmetric to the y-axis. But if we go to the origin, which if you graphed it, you see you do have symmetry with the origin. And let's show it. Every ordered pair xy produces the ordered pair negative x, negative y. Alright, so that implies y, well that'll be negative y, equal -4 over negative x. And as we simplify, right, this equation, we got negative y equal +4 over x. You say, well, that's different. We had y equal -4 over x. But what's different is both terms, right? Every term in this equation is different. So what happens this time is we multiply both sides by negative, which we can do. Once we multiply by the same number on both sides, multiplication, product, equality, we get right back to the original equation. Y is equal to -4 over x. There it is. There's our original equation. So we were able to produce it. So as we plugged in both test variables, right, x and y with origin, we get back to the original, which means we do have symmetry. This graph is symmetric to the origin. So does it have symmetry? Yeah, origin only. Origin only on this one. Now you can check it. Y equal -4 of x. Go to your calculator. Let's go ahead. This one's already in graphing mode. What's -4 divided by x? Here's this rational function, and you can see it's symmetric to the origin. Go to your table even a little further. Look at some ordered pairs. For example, what about the point 2, -2? Well, that's xy. Here's -x, -y. -2, +2. Right? 4, -1. Right? What do we have? -4, +1. Right? Any ordered pair xy, we'll get -x, -y back on that graph. So again, that's a quick way to look at it, right, as we check it out graphically. All right, now we're going to move on to our functions. Now, both of those equations happen to be functions, but not all equations are graphs of functions. But if we're dealing with a function graph, remember a function is a graph in which each x value has exactly one output y, past the vertical line test. Well, there's two types of symmetry with functions. You can have either symmetry with the y-axis, which is what we call a even function, or you can have symmetry with the origin, which we call a odd function. Now, they give us our tests. Well, they come right from what we just talked about. It says to find algebraically, or the graph symmetric y-axis, find f of -x. If f of -x, which is what? Taking out x, plugging -x. You remember y-axis symmetry, every ordered pair xy produces the ordered pair -xy. You plug in -x, and can you get back the original function? If so, it's even. Now, if it's not even, the only other possibility is origin. You're not going to ever have any symmetry with the x-axis, not with a function graph. Because if a graph symmetric to the x-axis, it fails the vertical line test, not a function. Now, in the origin test, if you remember our reflection points, xy produces the ordered pair -x, -y. We do the opposite with both. So we would find the negative of the function, which is -y, and see if it equals f of -x. Right, -x and -y have to hold true with that graph. So that's our algebraic test for even, odd, right, or has no symmetry, neither. So let's take a look. Let's go to some examples here. And we'll start with example A. So in example A, and we'll do our work down here below. So in A, I've got f of x equal to the square root of x to the fourth power minus 1. Now with that said, let's see if it's even. Is this a even function? I'm going to start with the even test first. I always do even first because you got half what you need for the odd test. But with that said, what are we trying to do? We want to know if it's symmetric to the y-axis, right? Every ordered pair xy, are you finding the point negative xy on there? And the test is this, right? If you want to do it with function notation, find that f of negative x, right? And if f of negative x equals f of x, it's even. So let's find f of negative x. That's step 1, right? Let's go get f of negative x back. Well, f of negative x is equal to square root of negative x to the fourth power minus 1. As we simplify based off that even power, this comes right back to the original function. So f of negative x ends up equaling f of x, which implies we have a even function. This graph is symmetric with respect to the y-axis. So again, you can graph it and see it, right? If you want to graph it, you're going to have symmetry with the y-axis. Y-axis is going to split it right down the middle. Want to check it. All right, now no need to test for odd. Can't have both y and origin. So this is a even function. Now as we go to example B, right, what do we have? We got f of x equal to 2x minus 2 of x. Well, if we want to look at our first test, is this a even function? Well, let's find f of negative x, right? Step 1, find f of negative x and simplify. So f of negative x is equal to 2 times negative x minus 2 over negative x. Out goes x, in comes negative x. As we simplify, we get negative 2x plus 2 over x, which is not equal to f of x, which implies is not a even function. So this graph's not symmetric to the y-axis. That means we move on to our odd test. Is it an odd function? Now odd is this. If what? F of negative x equal negative f of x. Right? It's odd. That's our question. So we want to find that. So we want to find our missing part. Let's find the negative of the function. So that's your work. So what does negative f of x equal? As we do that, we're going to take a negative 1 and multiply it through this function, which is the function of 2x minus 2 over x. As we distribute, we end up getting negative 2x plus 2 over x, which is not equal to f of x, but that's not what we're comparing it to. We're comparing it to what we just did earlier, right here. They're identical, right? They're equal. So yeah, we get exactly what we're looking for. It equals f of negative x, which implies this is a odd function, which means graphically it's symmetric with respect to the origin. Every ordered pair xy, negative x, negative y would be on it. All right, looking at example C, let's do our last one. Now example C, I've got what? A linear function, a line. Shouldn't take long to prove or disprove symmetry with this one. As we go to the even test, right, let's find f of negative x. Well, in this problem we're dealing with g, so we'll stick with the function name. So g of negative x equal negative x minus 2. As we simplify, that is not equal to g of what? X. So not equal to g of x means we do not have any symmetry with the y-axis, which means it's not even. Now as we do our odd test, we got to find the negative of the function, which is negative 1 times x minus 2. As we distribute, that's negative x plus 2. Well, negative x plus 2 is not equal to what? Here's g of negative x. Not equal to g of negative x. They're different. This is not an odd function. So it is neither, right? So in this example, we have no symmetry. So if you graph it, it's not symmetric with respect to the y or the origin. This is not an even or an odd function. So no symmetry with this linear function. But a linear function with a slope to it, with a slanted line, to have symmetry, you would have to pass through the origin, which means our y-intercept would have to be 0. With that, you would have an odd function. And of course, lines in which slope 0, horizontal lines, they're always symmetric to the y-axis. So yeah, we can have symmetry, right, with functions, but we don't with this one. So that's an example of each type you run into. Example of an even, odd, or neither. But that's looking at symmetry, and that's section 2.4. So I hope that helps you with this section.